Hoff equation. This equation gives the quantitative temperature dependence of equilibrium constant K. So this gives the relation between temperature and equilibrium constant. Before getting into the fine details of the equation, we will define important terms. Del G naught is the standard free energy change. R ideal gas constant. T temperature. K equilibrium constant. Del H naught is the standard enthalpy change. Del S naught is the standard entropy change. Already we have dealt in thermodynamics. We know that del G naught is equal to minus RT log K. So this log is base E, or we can call it as ln K. That means log with base E. This is log with base E K. Also from earlier topics, we know that del G naught is equal to del H naught minus T into del S naught. So del G naught is what? Standard free energy change. Del H naught is what? Standard enthalpy change. T we know temperature, and del S naught is the standard entropy change. So using these two relations we can derive the equation. So the next step will be substituting one first equation in equation 2. So we will be getting minus RT ln K. L means log with base E is equal to del H naught minus T del S naught. Since the left hand side is equal, we can equate the right hand side. That's what I have done it here. Minus RT ln K should be equal to del H naught minus T del S naught. This is the first step. Now we can rearrange. So rearranging, you keep this ln here and move this term to the other side. So what will happen is ln K is equal to del H naught by minus RT minus T del S naught by minus RT. So that is, this equation is divided by minus RT. So now we will get ln K is equal to minus del H naught by RT. Here this T and T gets cancelled, minus gets cancelled. Therefore we have plus del S naught by R. Now this is equation number 3. This is equation number 3. Okay. Right. Next step. Now differentiating equation 3 with respect to temperature. That is, this equation 3 is differentiated with respect to temperature. That is d by dt of ln K. So if you differentiate left hand side, right hand side also should be differentiated. So d by dt of minus del H naught by RT plus d by dt of del S naught by R. So this term, this del S naught by R is constant. So this is constant. The entire term is constant. So differentiation of constant is 0. So this value we can write straight away as 0. Now we will move on to the first term where we have minus del H naught by r as the constant, you pull it outside, minus del h naught by r d by dt of, here we have 1 by t. 1 by t can be written as t power minus 1. Because you are moving this t to the numerator, it becomes t power minus 1. Okay. So this t is goes to the numerator, it becomes t power minus 1. Now we have to differentiate it. Del h naught by r. Differentiation of t power minus 1 is minus 1 t power minus 1 minus 1, that is minus 2. So therefore we have this minus into minus is plus del h naught by r. Bring this t power minus 2 to the denominator, we have rt square. So left hand side, if you see, it is d by dt into ln k. So this is equation number 4. Now this equation is the differential form of Van Hoff equation. Similarly, we have integral form. Now you just look into the statement. D by dt of ln. Ln means log with base e. What is k? K we already defined, which is equilibrium constant, is equal to del h naught. What is del h naught? It is the standard enthalpy change, which is a constant, or ideal gas constant. So these two are constant. Now 1 by t square. So this term, the rate of change of rate of change with respect to temperature of ln k is inversely proportional to temperature square. So this is Van Hoff equation in differential form. Now we have Van Hoff equation in integral form also. So for that we have to use variable separable method. So now in this equation, what you do is, this is differential form of Van Hoff equation. Let me write down. So this is Van Hoff equation in differential form. Van Hoff equation in differential form. Next we will move on to integral form. So how to do integration, how to get integral form? First step what you do is move this dt to the other side. So that will be the first step. So you will be having differential of ln k. Ln means not natural logarithm is equal to del h naught by rt squared. We are moving this dt to the other side. So here you will get dt. Now next step what you do is integrating both sides. So integration is carried out both sides. Now what's the limit? k1 to k2. So k we already defined. It is the equilibrium constant. Now it has the initial value and final value. Similarly, if you come to the right hand side of the equation, the integration depends integrated with respect to temperature. Therefore, it will have some temperature T1 as the initial value, and you will be having some final temperature. So these are the limits that we have to consider. Next, the integral and differential gets cancelled. So the integral and differential gets cancelled, and you will be having ln k. So now you have ln k, that is log k. Upper limit is k2, lower limit is k1. Now already we have said del h, h naught and r are constant. You pull it outside. So del h naught by r is constant. You take that term outside. Integration of from t1 to t2. Now this t square is in the denominator. You move to the numerator. So it becomes t power minus 2 into dt. Now if we integrate, the value is del h naught by r. So integration of t power minus 2 is t power minus 2 plus 1. The same value put it in the denominator also. Since it's a definite integral, we don't include c. Okay. So del h naught by r is a constant. T power minus 1. Here again minus 1. With upper limit t2 and lower limit t1. Now bring this minus 1 outside. So minus del h naught by r. Now this will be minus, so t power minus 1 can be written as 1 by t. Upper limit is t2 and lower limit is t1. So the formula is minus del h naught by r, upper limit minus lower limit. So upper limit is t2, so 1 by t2. Lower limit is t1, so 1 by t1. Now this will give you minus del h naught by r. You take the LCM, so t1, t2 is the LCM. You multiply here, cross multiplication, t1 minus t2. Okay. Now what you do is, move this minus sign inside. So what will happen? See, left hand side we are having ln k. Upper limit is k2, lower limit is k1. This we should not forget. Now here again, upper limit minus lower limit, left hand side is equal to, you move this minus sign inside. So what will happen? Del h naught by r, this t1 will become minus and this will become plus. So we can rearrange like t2 minus t1 by t1 t2. Now if you come to the left hand side, upper limit is k2. You substitute here ln k2 minus ln k1. Okay, now we all know the relation log m minus log n. So we can write it as log m by n, k2 by k1, which is equal to del h naught by r into t2 minus t1 by t1 t2. This is equation 5. Okay. So we are substituting the upper limit minus lower limit and we are getting this relation. This is integral form of Van Hoff equation. So this is integrated form of Van Hoff equation. So that's all about this topic on Van Hoff equation. We have derived both in differential form and integrated form. Both the results are important. Thanks for watching this video. Nandri.